Proposition 3, things that have nothing in common with one another, one of them cannot be the cause of the other. Proof, if they have nothing in common with each other, then, by Axiom 5, they cannot be understood through one another, and therefore, by Axiom 4, one cannot be the cause of the other. Q.E.D. This theorem, that causality does not hold between two entities that have absolutely nothing in common, offers important insights for complex systems, complexity education, and everyday judgment more broadly. To assert causality, levels of explanation and forms of representation must interlock, and at a minimum one must secure attributes, scales, and representations that can be mutually mapped. Rather than directly linking microscopic interactions to macroscopic patterns, one should first establish intermediate-level variables, such as statistical measures or network metrics, to build a bridge of commonality. Moreover, the state variables of a model and the observables of reality must be isomorphic if the model's causality is to project onto real-world causation. Attempts to explain reality with abstract variables that share no common dimension readily lead to category errors. In complex systems, causation typically proceeds through mediation and intermediation, with mechanisms such as network structure, feedback loops, and critical points connecting the pieces. Accordingly, rather than hastily seeking direct causation, we should first identify the mediating variables that provide a common dimension and construct chains of indirect causation. Instead of directly connecting terms from different categories, normative and descriptive, semantic and physical, qualitative mental properties and geometric properties, we should first examine whether they can be mapped into common variables that translate between them. In educational settings, one can train learners to describe a single phenomenon at micro, meso, and macro scales, and to specify the linking variables that connect these scales. For example, after describing crowd movement in terms of individual rules, micro, local density and flow, meso, and overall congestion, macro, one then checks the correspondences among them via equations or simulations. At the same time, learners develop the capacity to design which variables share a common dimension by using criteria such as units and dimensions, time, space, energy, information, measurability, variability, and network distance. For model validation, it is important to triangulate and cross-verify different representations, differential equations, agent-based models, network models, and experimental data, using common indicators, for example, clustering coefficient, correlation length, entropy, R0, and to withhold causal claims when such common indicators are absent. When importing concepts from other fields, we should emphasize the role of a conceptual interpreter who translates terms into common variables and quantifies them, rather than borrowing terminology as is. For instance, resilience can be defined, from a network perspective, as the proportion of connectivity retained after node removal, and from a dynamical perspective, as the time to return to steady state after a shock, thereby making the notions compatible. Consider real-world cases. In public health, rather than asserting a direct causal link between viral transmission and the spread of rumors on social media, it is more appropriate to map them onto the common property of contact network structure and then model indirect pathways via mediating variables such as the distribution of contact degrees, hub nodes, and mobility indices. In urban policy, before assuming a direct causal relation between variables from different categories, such as rising crime and weather, we should construct and test mediating variables on a common dimension, such as nighttime activity, illumination, and police visibility. In educational assessment, instead of directly tying teaching style to creativity, we relate them through learning dynamics variables such as task difficulty fit, interaction density, and feedback delay. In corporate decision-making, before linking heterogeneous categories like brand image and supply chain resilience, one should define indicators on a common dimension, such as trust capital, the betweenness centrality of partner networks, and information sharing latency. On the practical side, before making a causal claim we should check, in order, whether the variables are on the same scale, whether scale transformations, aggregation/disaggregation, are defined, whether units and dimensions are compatible, whether measurable common indicators exist, whether mediating variables and pathways have been specified, and whether alternative routes, such as confounders and common causes, have been examined. Conversely, when rejecting a causal claim, rather than simply declaring there is nothing in common, it is more persuasive to present counter-evidence showing that no explanatory power emerges even when one constructs possible common dimensions or mediating variables. This principle is also useful in life. It helps us curb the habit of hastily linking phenomena from entirely different categories and jumping to causal conclusions. And in collaboration it reduces misunderstandings by first agreeing on common vocabularies and measurement indicators. In problem solving, rather than forcing variables from different categories and scales to fit together, it is crucial to design the intermediate pieces that connect them, that is, the mediating variables. In addition, we need a balanced attitude that broadens the scope of inquiry with the humility of saying we have not yet found a common dimension, rather than they are not connected, while guarding against unfounded causal assertions. In the end, causation holds only on shared dimensions, properties, and scales. Because in complex systems such commonality is hard to find directly, we must build bridges of causation through mediating variables and mid-level modeling. In education and practice, the core competencies are precisely the design of such common variables and the securing of scale compatibility, and that is the practical meaning of this theorem in today's complex world.